Good afternoon, everyone. My name is Josh Griffin, and I manage a team of performance engineers at SAS. Internally, we refer to as the speed doctors, and we work really hard to improve our analytics by doing deep dives into hardware and trying to harmonize the software with the hardware across CPU, GPU, and more recently, QPUs. So partnerships like this are really exciting for me in particular because we found time and time again that when you have experts from analytics, infrastructure, software, and hardware, all speaking the same language, true magic can happen. So I'll start with describing the analytic or the architecture of VIA so you can best know where to apply the information that you would learn today. So when you log on to VIA, unbeknownst to you, even though you're on your desktop, we'll actually give you a compute node all your own. This is called the Spree node. This is where most of your SAS 9 analytics will initially run. And if someone else comes on, they'll get their own node as well, disjoint from the others, and so on. And the true magic happens in VIA when you call our so-called VIA procs, because they're going to, under the hood, call our cloud analytics service, which is a very powerful distributed system that can solve basically any size problem very quickly, efficiently for you. More recently, since the size of nodes have grown, we've combined that and simplified the format. This started in the workbench, but has since progressed throughout VIA. And now when you log on in the ECE mode, you're going to get a node that's going to do everything for you. So that CAS server is hidden, and it's yours, and you probably won't know it's there, but it's going to make your analytics be far faster. Same as if you did SMP mode for a CAS server. And so if one node is enough, that's great. And so the punchline, the reason to tell you this is that what the speakers are going to talk about today is really going to apply to ECE and CAS servers. That's where the heavy lifting analytics occurs. So why is performance so critical? Well, if you've ever played around in Model Studio, you'll know that by simply dropping your data set in and flipping a few switches, you can get pipelines like this. Why do we create pipelines like this? Well, given a data set, it's impossible to know beforehand whether neural net, logistic regression, forest, decision tree, gradient boosting is the best. And on the cloud, you can run them all and be almost like a clairvoyant where you get the best in the same time it would have taken you to run one of these models because they can all go at the same time. In addition, things can invert where the defaults for neural net might be better than gradient boosting, but with minor hyperparameter optimization, it might be that gradient boosting is actually the best for your data set. And so in addition to running these models in parallel, we'll run hundreds of instances in parallel. That means with very little effort on your side, you're getting hundreds to thousands of jobs, and all of these in the cloud can run in parallel and give you data back almost as if you were just doing a few in a row. And with the advent of agents, more and more we're going to see agents crop at important intersection and decision-making points all throughout our software. And that means you're going to get better decisions, but also many more decisions than you had before because they're going to think of things that a human didn't anticipate. So that means the number of jobs that you're going to be able to submit of high quality is just going to grow exponentially in this new age. And you might say that we're just randomly shotgunning things out, but I'd argue that what we're really doing is kind of putting the scientific method on steroids. The scientific method, what does it mean to follow the science? It means if we have a hypothesis, we don't sit in our rooms and argue who's right. We actually create an experiment, run it, measure it, and let the results dictate what is the ground truth for this problem. So in the past, science had two bottlenecks, and I'd argue earlier this first one was the major one, in that probably most of the time the compute that you did have was running idle while you're thinking what to try next, make sure you're not repeating, running in a circle, and looking at the results and deciding how to interpret them. But now with AutoML algorithms and agentic AI, this has pretty much been eliminated. You can, of course, give the agents inputs and have, put your thumb on the scale, but in general, you're going to have an endless line of really promising ideas to try. So the only really bottleneck that you're going to have is the compute. The faster that you can cycle through these ideas, the faster you can find the proverbial golden needle in the haystack. So really, this is the true bottleneck of science moving forward at this moment. And that's why performance is so key. And I'll pass to Vijay at this point.
Thank you, Joshua. It's a great privilege to associate ourselves with Google and SAS in one place. And of course, Intel is everywhere. This is an example of one of the clouds where we have done some work. SAS has taken some of their dearest workloads and tested, benchmarked them against our latest CPU-based instances. Our latest CPU is Xeon 6. The C4 is the latest widely available Xeon 6-based CPU. Recently, I'm actually traveling from Google Next conference to here. We actually had few additional shapes and types of instances are available. I'm going to talk to you about that. But I want to just highlight some of the relationship that we have with Google at large. Google was first to come up with, come to the market with our Xeon portfolio based instances all the way from first generation to Xeon 6, our latest generation of CPU. And Google also uses our infrastructure processing unit IPU. And of course, create usage of IPU to, for them to make a big difference in the way these instances are configured. Some of the offload mechanism of the run-of-the-mill server processes to IPU in such a way that your vCPUs that you're using in the cloud are most effective for your workloads. One of the testimonials of our recent announcement of our re-energized relations with our Google. This is one of the statements from their SVP. Xeon CPU, IPU are the present products that we are actually Google Cloud uses, and of course, Google's own services run on Intel. Some of the SaaS services depend on storage. Some of those things are, and of course, Intel infrastructure is everywhere. Going forward, I'm sure this deepened relation will bring more options and products that can be used in Google Cloud for the solutions like SAS. So I was just talking about newest instances that were announced. Series of C4 instances with Xeon 6 were limited to 128 core and above large shapes, and smaller shape with LSST still recently. With this announcement, Xeon 6 is an option that you can actually do with a min CPU option to pin the CPU to be Xeon 6 for wherever you can configure and you need Xeon 6 performance. So that means C4 is widely available with all shapes and sizes now. On top of it, C4N is the latest announced network optimized instance where it's just not network, but also the I/O bandwidths and the hyperdisk matching, highest performing hyperdisk matching is now part of the C4N series. I'm sure Brooke will expand upon that. We have some specialized instances like Z storage optimized instance. Z4 instances are on preview now. M4N instances, memory optimized instances with large scale in-memory databases are some of the SAP, Redis kind of usage. And now we have a specialized instance that's on preview right now. So just to give a kind of holistic idea of all the types of instances, Intel-based instances available in GCP, I actually wanted to show you that there are instances running all the way from our first generation Intel Xeon all the way to the 6th generation. And based on, this is one of the use cases where ISV has tested their workloads and actually trying to show you the delta in value in terms of improved performance, TCO, when you're actually adapting latest and greatest from Intel in GCP. Xeon 6 we've been talking about. Xeon 6 has been evaluated by SAS, and in GCP, C4 instance is what was tested out. some of this kind of holistic workload boost that we are getting over gen over gen, it actually shows with limited users to scaled user benchmarks where the performance here up to about 51% improvement in performance compared to N2 instances, which are about 2 generations old. And also, it also shows that when you scale the workload on a given SAS VIA instance, the performance is still remarkable at 45. That means the performance scales as you scale your platform. So the latest Xeon CPUs actually have newer technologies built into it. Since our 4th generation, we have something called advanced matrix extension. This is an accelerator built on is on each core of this Xeon 6 CPU. That means this accelerator is not a co-accelerator sitting aside on a socket. It's sitting on each of your core. As big as, let's say, 128 core system that you're using, you have 128 accelerators working for you. This is specially made for making the performance of matrix multiplication operations, which are typically needed for deep learning workloads. It's a simple math. Actually, complex math that CPU solves. Deep learning only requires simple math, addition, multiplication kind of things. Now, by having the accelerator sitting on this core, the deep learning workload strings are now addressed by this accelerator. You can get anywhere from 3x to 6x performance for those qualifying workload strings. So till recently, we actually supported BF16 and int8 data types for quantization. With this generation, we added FP16 as well as a qualifying data type. So how this is different from how the processing on CPU is there. So we actually have a newer instruction for matrix multiplication, Timo. And then we have tiles, a different way to represent the data. That means the zeros and ones that are used for representing data in a vector, for example. You have 512 bits where you can pack as many data elements into a vector. You can actually process all those data elements in one instruction. Here we are taking next step. We are representing data in tiles, basically imagine array. And we are able to address each tile, and we are able to add or multiply these tiles to another tile. So we have provided those tiles on the CPU core. Using that space to store the data, using the newer instruction, we are able to now get the performance boost I just explained. So this slide actually shows the quantization options that you have. For example, if you have AVX12-based FP32 compared to AMX BF16 or FP16, we have seen in our labs up to 16x performance boost. AVX 512 with int8 versus AMX with int8, we have seen anywhere upwards of 8x performance boost from this technology. And actually, there are few white papers I would encourage for you to go to read so that you actually get the confidence over this technology, how dynamic and transparent this technology is. Intel continuously works with our open frameworks, AI frameworks, and we are working with SAS. Presently, our compiler enablement is going on. Past that compiler upgrade, SAS will have the ability to use this accelerator within SAS VIA. With this, I'll just pass on to Brooks. He will expand upon how Intel is present in GCP and what are some of the observations on different instances that makes it as a unique capability that you can use on GCP. Thank you.
Thank you, Vijay. Hi, I'm Brooks with Google Cloud, and I am proud to be here with you today. I'm a customer engineer, and I'm going to talk about C4 on Google Cloud. So what we are looking at here is a fairly comprehensive spectrum of workloads as we see it at Google. So from left to right, it really breaks down to general purpose and specialized. At its core, that's really where they live, and the C-Series focuses on that consistent high-performance benchmark that we need to hit for certain workloads. So digging in, you can see the drop-down that we see C3 and C4 under that C-Series. As we look into general purpose and zoom in a little bit more, we really have the N and the C-Series. And so the N-Series kind of won our hearts, as I like to say, just due to its price performance and its flexibility. So they go there for standard GKE nodes and random workloads that you need cost optimization and flexibility as kind of a paramount metric. But when you really need top shelf performance and a consistent high performance benchmark and control, we're urging customers to look at C4. Customers say to me, and they say, well, why don't we just get a standard sized compute node and then we attach a GPU? Couldn't we attain more? And my answer is not necessarily, right? So at Google, we like to take a step back and tell a story about AI workflows. And here's a sample one. I might be in the market and I need to get a high-rated waterproof running jacket. Under $150, let's say I wear a size medium, and I want to check the local downtown store, see if they have what I want in stock, make sure it's well received by the other public, and then reserve it, buy it, and send me the confirmation, right? So as a human looks at this, we have our foundation, we have our brain, right, kind of on the left, and then we kind of have our process on the right. So when our brain takes in information, we apply critical thinking and critical problem solving to that, and then we kind of continuously learn, right? And then on the right side, when we get a prompt for something, a challenge that we need to do as a human or a computer, we kind of look at different loops and we kind of have a process for this. And so we break this down. We got to understand what is being asked of us or for us and break it down. Like, what do we know about this? Well, I know I need a rain jacket. I know that I wear a size medium. I know that I like the downtown store, for example. And then maybe what I don't know is if they have it in stock, if they have what I want, if it's available for pickup today. And so we have this loop and this little process that we as humans do is checking the inventory, looking at the ratings, purchasing it, and get a confirmation. If we think in terms of infrastructure, it's actually a very similar process, right? We have these loops. I color code this to highlight where are CPUs being used and where are GPUs being used. In today's age of inference, we're seeing more and more resources on the right-hand side. We're seeing more and more CPUs being used on the right-hand side of things. And so it's not necessarily a 1 or a 0 to use a GPU for high-performance applications or not. They're intertwined, and so you see a lot of green over there where the C4 plays quite well. And then also on the bottom left for reinforcement learning. But it's a similar type process when an agent or an AI workflow takes a process. So zooming back into the C4, you choose it for 3 real reasons. Like the 3 pillars I put up would be, if you need this performance optimization, where you get rid of noisy neighbors or you avoid them as much as possible, you get this NUMA locality, which I'll talk about in a minute. You need these enterprise features. So with the Titanium architecture, we can offload storage tasks, networking tasks, even security tasks to hyperdisk. So it's kind of offloaded. The CPU doesn't have to deal with it as much. 200 gigabits per second networking, what can we not do with that, right? And then we can look at VIA for things that need high performance, workloads that do AI, ML, and inference, and things like that. So that's kind of where we like to take customers. Digging in architecturally, right, with placement, it's a big thing that is needed for this size of a workload. So if my laser works, we have placement that works, right? So the C4 shapes align from the host to the guest each time, whereas in the past you may not have always had that. And so there's latency, and there's maybe issues down the road with that. But we can guarantee that with the C4 series. So virtual NUMA is something that's guaranteed. Also guaranteed is maintenance expectations. You boot up a VM of C4, and you know that within the first 7 days, there will be no maintenance tasks ever for that instance. After 30 days, at least, again, we'd have to give a 7-day notification window before anything comes up on that. So you have expectations. With the N-Series, for example, you get that cost optimization, but you don't necessarily get these guaranteed maintenance requirements. With placement, again, when you have a high dense workload, placement matters. And so putting them together for low network latency is going to be paramount, right? So if you have 3 zones, you can set a policy in place to say, you know what, no more than 1 or 2 zones away, or no more than 0, for example. So you can make that as compact as you want, and that's control you have. Also with turbo frequency. If you need predictability with your gigahertz and your timing, you can guarantee that 3.9 gigahertz as opposed to the occasional 4.2 gigahertz. So how do we compare? Like, we're seeing substantial benchmark gains from our previous C3 series. Head-to-head with another hyperscaler, off the bat, we're seeing a 13% price performance gain. I love Sas's quote here, just talking about GPU comparable performance down here on the right. When you get into deep learning and data generation of synthetic nature, you're looking at a potential 20% improvement. So digging deeper, for these ML workloads, like recommendation, we're seeing a 60% performance gain. And then, Sas's quote is a great neighbor to some of the other customers that we're seeing velocity, just general velocity, and then latency improvements from 50 to 70%. So I'm going to hand it back to Joshua to bring us home for more benchmarks to SAS.
Okay, so today I'll be going over 2 different benchmarks. My team did not do these, so I'm trying to do them justice. Sadly, they could not be here, but they worked very hard on both, and I hope we'll have important insights into both of these cool new technologies. So I'm going to start with comparing the N in C series, and this was done inside of VIA for this team. And we used SAS VIA 2025-09 LTS release. We used identical cache topology, so the only difference was swapping in C4 for N2, 32 vCPU instances, and 256 gigs of RAM, and this was SMP, so you could also have done got the same results for the ECE mode mentioned earlier. And we had multiple iterations to mod out for outliers. And we focused on typical top K, what you're most likely to do on a day-to-day basis outside of deep learning with these workloads. Forest, neural net, gradient boosting, support vector machine are kind of like the top 5 technologies, and we did a reasonable number of options. We chose 2 data sets, one with 6 gigs, the other with 38 gigs, with 1 million and 5 million observations, respectively. And we picked ones where the memory and the compute were the dominant factors, so we could really study the benefits of C4 on those instances, and we believe this is representative of real-life CAS usage. So I know this is a lot to take in, but if you just look at the red and the green, the red is going to be for the N series, the green is for the C series, and if you look just down the line, eyeball norm, and I'll go deeper in other slides, you can see you're getting roughly a factor of 2 across the board. We're also looking, as we add more users, to share that same instance, and the extra load and the elongation of time, and you're seeing that it's less exasperated on the C4, so you're getting a better shared experience when you're both logging on at the same time to do your analytics concurrently. And we spread it out across the different phases from data prep to training to scoring, so you can see how each phase is affected. I know this is a giant table. I'm just putting this here so that if you wanted to drill down later, we can, but I've tried to summarize it succinctly by adding these times in terms of the time for data prep, time for training, time for scoring, and then total altogether. And this is, again, dark blue is 1 user, Medium blue is 2 users, and light blue would be 4 users. And you can see that the time climbs as you increase the shared load on the system. When we move to C4, you see a dramatic drop, about a factor of 2 if you look eyeball norm, and I'll show later, drill in on that. One thing I wanted to do in particular is that if you look over on this light blue column here, and then look at this dark blue column here, they're roughly the same, which means that 4 users are using the same machine and being able to do the same, basically 4 times the work in the same amount of time, which is pretty remarkable. This is for the 5 million data set. Again, just throwing up to you so that you know it exists, and we could drill down into it by the numbers. Again, summarizing into data prep, training, scoring, and total. This is for the N series and same story. So we just want to make sure as we continue to climb that we're seeing the same trend. And it's pretty clear that, again, you're getting about a 2x performance boost across all the dimensions, from data prep to scoring and from 1 to multiple users, which is really great to see. And you think of this in terms of elongation of time. You can do in 2 weeks what maybe, and this slide says better, would normally have taken you a month. And if you have competitors, if you're twice as fast as they are, the gap between you two is just going to grow astronomically over time. So this is really powerful news. And so this is, on the x-axis is the speed up factor, on the y-axis is the number of users, and then the different colors are for the different phases of the machine learning. Main key takeaways, everything is hovering around the 2x faster. And so just in summary, advantages seem to increase with larger data volumes. The overall speed up is around 2. Forest and gradient boosting, which tend to be the most popular models, was greater than 2x faster. So that's really cool to see. The total runtime, again, reduced by about a half. I like to think of it in terms of if you were to, buy something once and it's 50% off, that's really great. But if you're doing this thousands of times, that's a huge gain. And when you're doing these large pipelines, you're repeating this process over and over again. And only minor anomalies, so it's really safe for our customers to switch it out and they won't see churn in the results. Overall, the take-home summary is C4 is the preferred platform for CAS and ECE, superior scaling with users and data size. And we have high confidence that if they swap this out, everything will run the same, it's just going to be faster. And of course, we would love to do future explorations and deeper dives to find other interesting analyses. So I'm going to switch to deep learning, and this is a team that works on edge computing. So this was not in VIA, but the summary and the results should still translate. And this team focused on ResNet and DC GAN, both training and scoring. And so first, if you look at this one on the left, this is bfloat 16 and floating point 32 compared to the baseline. And the average over here, you see about 8x to 6x speed up out of the gate, which is really cool to see. And ironically for this one, we see that GPU is a little bit ahead for a batch size of 32, but as it climbs, it's clear that the bfloat 16 is outpacing the GPU. And by the time we got to batch sizes of 256, they were over their memory limit and couldn't run it all. So it's a clear winner for AMX for this one. For scoring, we see that bfloat 16 was definitely running ahead at a 44x, which is amazing. So that's definitely would be the choice if you can to do the scoring. But you're still getting 12x speed up out of the gate for FP32. So if you just close your eyes and we're looking at bfloat, that's still impressive. GPU is doing great for scoring on this one. But you can see that gap tends to go down as the batch size increases. And by the time you get to 248, you're actually beating the GPU, which is pretty amazing to see, given that early reports are always like this 100x faster than CPU as a rule of thumb, and we're not seeing that anymore. Training for the DC GAN models, again, we're getting an average of 4x speed up over the baseline. Across the board here, there's not much difference between BF16 and FP32. The GPU is doing really well on this model type, But if you look, you're really on an order of about 5x faster, not that 100x. And you have to take in mind the cost differential between those modalities and make sure that you feel the juice is worth the squeeze on this one. And this is inference on the DC GAN models. And here we get around 5x speed up for bfloat 16, 4x for floating point 32, fairly similar. And then the GPU is 14x. So still faster, but you're looking at, with respect to BF16, a factor of 3, not 100. So again, that's close enough to make it hard to argue for that price differential, in my opinion. Summary for this study is the speedup is significant for training deep learning models for both scoring and training. bfloat 16 was definitely most impressive, but if you weren't studying that and just looking at the floating point 32, that's still very impressive results in my mind. And for large batch sizes, we are seeing AMX break away and surpass the GPU for these studies. And so in closing, again, just to hint at the importance of having groups like Intel, Google, and SAS talk to each other, make sure that they're leveraging the full power of the analytics and everything is hooked up correctly, so there's no low-hanging fruit performance gains that you can have very easily with nominal, if no, increase in cost. And I'm hoping that this partnership will continue to blossom and grow, and a lot more should come from it. Here's our emails. Happy to chat later, and thank you for your time, and we can answer any questions.
All right, thank you so much. We have about 9 minutes for questions. Anyone has a question?
So maybe I can start, maybe you can add. SAS preferred way of providing the capacity to the customer is through their SAS managed service. And with the SAS managed service, presently SAS own engines is what you have seen with and without AMX utilization. These gains can be realized right now with right instance mix. In this case, it will be C4.
Yes. Yes, transaction through the marketplace is available. Talk to your SAS account manager for getting that hosted on Google Cloud and transacted through the marketplace. Yes, 100%.